Welcome to CSAI Think Tinker Learn. This is this episode is one of the episode from my System Design Essential series. The goal of this series is to give you a solid mental model of complex system design topics without all the fluff. Today we are unpacking object storage. If you want any detailed design or any detailed deep dive on any of the topics related to this particular video or any other videos, do let us know in the comments. We'll try to put a deep dive on that. Let's get started. To understand why object storage exists, we have to look at what it replaced. Legacy hierarchical file systems. The nested folder we use on our laptops. Break at scale. In a hierarchy, every subfolder requires a lock. As you scale to trillions of files, walking the tree creates physical bottlenecks and lock contention hotspots. Object storage utilizes a flat namespace. Think of it as a library of everything. There are no nested folders, only petabytes of unstructured data accessed directly via unique key. This allows for a near infinite horizontal scaling. The atomic primitive of this system is the object. Unlike a file, which is just a sequence of bits, an object is a self-describing resource. It consists of three layers: a globally unique ID like UUID, rich metadata, the catalog card that enables search and access control, and the raw data payload. The self-description is the secret sauce. It transforms opaque binary blobs into manageable, searchable resources that the system can automate. How do we find one specific object in a sea of billions? We bypass the ON linear search catastrophe by using metadata index. The system uses a distributed key value store to map an object ID directly to its physical location, the specific node, and the disk offset. However, this index is a critical failure domain. If the index partition drops, your data is effectively orphaned, even if the physical disk holding the video or logs are perfectly healthy. The baseline for durability in a distributed design is 3-time replication. The goal is simple: protect against inevitable hardware death. When a put request arrives, the system replicates that object 3 times across 3 failure domains, different racks, or even different buildings. The problem? This creates a massive storage multiplier. 1 petabyte of data requires 3 petabytes of disk. At exabyte scale, this capital expenditure can bankrupt a company. We need a more efficient way to stay durable. The fix for that cost problem is erasure coding algorithm, often seen as 4 plus 2 scheme. Instead of cloning the whole object, we break it into fragments and add parity fragments. The math is brilliant. Any K fragment can reconstruct the whole object. In a 4 plus 2 setup, you can survive 2 simultaneous node failures, but only require 1.5 times raw storage instead of 3x. The trade-off? You trade disk space for compute overhead, as your CPUs must calculate complex parity matrices on every read and write. Physics eventually catches up with us through network latency. In a distributed system, network delays can cause replicas to briefly diverge. This creates a stale read trap. If a client performs a put on node A and immediately tries to get that object from node B before the sync finishes, they will receive an old version or a 404. This breaks the read after write expectation that most developers rely on. We fix this by choosing where to focus our consistency. For new object, modern systems like AWS 3 now offer strong read after write consistency. The put operation takes a write lock and ensures all replicas are synced before acknowledging success. However, for overwrites or deletes, many systems revert to eventual consistency. They prioritize availability, allowing replicas to converge over a short window to ensure the system stays fast under heavy load. When designing your application, you must respect the API access patterns. For ingestion, never try to send a 50 GB file via a single put. You're guaranteed to hit a timeout. Use multi-part uploads to send parallel chunks. For retrieval, use range gets to stream specific byte ranges. For control, leverage the head object call to check metadata without the cost of downloading the entire payload. Not all data is equal. Object storage uses lifecycle automation to move data down a temperature funnel. Hot data lives on expensive NVMe drives for millisecond access. As it ages, policies move it to warm HDDs and finally to cold archival tiers like Glacier, where it might live on tape. Beware the retrieval latency trap. Trying to synchronously fetch a cold object will stall and crash an application that expects immediate responses. In a shared flat namespace, security must be built in concentric layers. We have TLS for transport, IAM bucket policy for access control, and the final boss, warm blocks. Write once, read many. Warm blocks physically deny deletion at the disk controller level for a set duration. This is the ultimate defense against ransomware. Even if an attacker gets your admin keys, they cannot delete the data until the timer expires. The true power of a modern object storage is that it has become a universal substrate. The architecture is language agnostic. Whether you are using Python, Go, or Java, you're likely interfacing via the standardized S3 API. This allows you to move between AWS, MinIO, or Ceph with a minimal code changes. Just remember the senior engineer's rule. Always handle your HTTP exponential backups at the client level. Let's synthesize the critical path of a single write. Your SDK fires a put, IAM validates your identity, metadata index finds an available slot, and the object is split via erasure coding. The fragments are committed to physical SSDs. Understanding this flow helps you diagnose exactly where a request is hanging. Is it an auth delay, an index lookup, or a physical I/O bottleneck? The mental model for object storage is this. It is optimized for limitless horizontal scale and its durability, not transactional speed. On our trade-off chart, you can see it excels at throughput and storage cost, but it struggles with latency and compute overhead due to erasure coding tags. It is a warehouse, not a high-frequency trading floor. Use the right tool for the job. Object storage abstract away the hardware, but the physics of the network still apply. Design for failure and automate your life cycles. Now, I want to hear from you. In what scenario would you choose free-time replication over the more efficient erasure coding? Is it for low latency or purely to avoid the compute overhead? Let me know your thoughts in the comments. If this overview helped you, please like, share, and subscribe to CSAI Think Tinker Learn. Check out the full article on the site. Thanks for watching and see you in the next